we're going to kind of go through the history of cellular, because I think that will help explain a lot of things. You know, a lot of times I get asked, what is the core for? Why do we need this? So I'm hoping that, you know, looking from starting with 2G and evolving from there, that hopefully that should help, you know, explain the reasonings for everything. Okay, so starting with GSM, this was initiated initially by ETSI, which it was in Europe, and they had a goal of connecting or globalizing the standard, especially in Europe, as they were all using different techniques. So traveling between countries meant having to use a different phone. So at this time, everything is circuit switch based, so there's no packet gateways or anything at that point. They technically did have data, but it required that a dial-up be created for any user that tried to access the internet. And at this time, they used TDMA, which was an FDD based, and they had 8 channels, or 8 slots, per channel. And the frame was roughly 5 milliseconds. All right, so the architecture of the GSM core is actually very similar to what we have today with LTE. It was called different terms at that time, but they basically broke it down into the mobile station, which is now called the UE, the base station subsystem, which is now called the UE-TRAN, and the NSS, which we call the core network these days, and the OSS for management. And yeah, we'll move on to the next slides that go more in detail on this. So with the BSS section, it's pretty simple. You had just the mobile equipment, and then you had the base station equipment, which was separated. So you had the BSC, which we call the RRU, which does the radio side. You had the BTS, which is the BBU, and the equipment that you guys are deploying for us, it basically integrates all this together. And at that time, what they called the NSS, it's very similar in the sense that they have the MSC, which is very similar to what we have as the HSS. And the databases, the database for the HSS, and they basically had a bunch of different databases at this time. And that's pretty much, for the most part, integrated today. So when data was finally introduced, they did this by adding on a packet gateway to the existing infrastructure. So basically, the data packets traveled through there, and then everything was still circuit-based for the voice. And this was basically the first iteration for non-circuit-based data. All right, so finally they introduced more MCS levels to get better data rates. And now when it shows the peak data here, this is assuming that they're getting full airtime. So if all 8 slots were assigned for a full second, they'd get 473 kilobits per second. But ideally and realistically, it was more like dial-up or worse. Okay, so that's when 3GPP came together. And the idea of 3GPP was to create a 3G standard, which eventually evolved where they would take in GSM, and it was also creating the 4G standards as well. And from here, we switched from TDMA to CDMA. Now, at this time, throughout most parts of the world, GSM was taking off. But here in the US, we were using different standards for the most part with the IS-95. And the US was kind of the innovator with CDMA. So eventually, 3GPP came out with their version of CDMA. Okay, so the ITU basically came out and they wanted companies to submit proposals for 3G. And yeah, basically you can see the list here of what was finally approved. So for 3G, they basically wanted that for fixed wireless that you could reach up to 2 megabits per second, and that in the vehicle you could get 144. So these are the standards that eventually got approved. And at this time we have, in the US where they were doing the IS-95, they ended up becoming a company for 3GPP2, and they worked on a different standard for CDMA 2000. So we're going to follow what 3GPP went with the UCDMA. Okay, so yeah, here again, kind of overview what the standards which were finally approved. Skip over that. Okay, sorry. So here we have WCDMA. And this is basically the start of 3G. So here they used a direct spread spectrum, and they used 5 megahertz channels. So anyone deploying this basically had that one channel size. And for data speeds, you could reach up to basically 2 megabits per second. All right, so this is what they kind of call 3.5G. They had HSPA, and AT&T was basically one of the first operators to deploy this. This is where they introduced 16 QAM and very short transmission times, fast scheduling, improved retransmission techniques, which basically ended up with about 14 megabits per second. So some of the techniques that were involved here I'll highlight because these are the same things that are being used in LTE today. You have the link adaptation, which was able to send CQI from the UE. And you have fast dynamic scheduling, which basically at this time, to help make lower latency and better throughput, before all the scheduling was done in the core. So at this time, they moved the scheduler to the actual, what we call the E node B now. And then they had HARC for better error corrections. And again, this was moved from the core to the E node B. And then finally, with 3G, they had the 3.75G, and they were able to get up to 42 megabits per second. And they introduced dual carrier operations as well, and up to 64 QAM, which we're seeing today with LTE. And you'll notice through the history here, you'll see the different release numbers. So this was with release 7, and the release after that, starting with release 8, is when we get into LTE. Okay, so then the ITU, again, is now asking for 4G, and the requirements they listed for at that time was that for fixed wireless, that you would be able to reach at speeds up to 1 gigabit per second, and for mobile operations up to 100. So the story on this is that when LTE initially came out, it technically did not meet the 4G standard, since fixed wireless could not reach up to 1 gigabit per second. But they still marketed it as 4G, and eventually they allowed the marketing usage for 4G. And when we get into LTE Advanced, when you can finally hit 1 gigabit per second, they usually call that true 4G. Okay, so now we'll go through a high-level overview of the LTE, we'll call LTE fundamentals. Okay, so when the 4G work got started, 3GPP basically put together 2 groups, one to work on the EU TRAN and one to work on the EPC. Together, this is called the EPS. And this is, it completed roughly mid-2006, and this is when release 8 comes out. All right, so some of the features and changes is it went from CDMA to now we're using OFDMA for the downlink. And when they found a lot more advantages when you're pushing a lot of data with OFDMA. So what that means, though, is since it's not using CDMA-based, the radio interface has to be different. So generally, they would deploy this in addition to the current 3G that's being deployed if you're as an operator. Okay. So one thing that's a bit different is the uplink. The uplink uses a flavor of OFDMA, but the challenge at this time was trying to find how to save battery life. So what basically they're doing with here is they're able to get lower peak to average power ratio, which was an issue with OFDMA. So the reason that the uplink and the primary reason of that being slightly different is to save battery power. Okay, so in LTE, you have different transition modes, and I kind of bolded the ones here of importance because these are the main ones that have been used with LTE standard. Transmission mode 2 means that you use multiple antennas, but the downlink doesn't use multiple layers, so it's able to get better signal with multiple antennas. Transmission mode 3 is what we're all using today with the Baicells equipment. This allows for basically what we know as MIMO operations, so you can get 2 data streams from 2 antennas. And then we have closed loop, and the main difference, you'll see transmission mode 3, transmission mode 4. They're very similar, except that closed loop is able to provide more detailed information and can potentially get a little bit better throughput. You'll also notice things such as multi-user MIMO and beamforming, but when this was introduced, it was very expensive, and people generally skipped this and waited for LTE Advanced before implementing those other features. Okay, so being a flat network basically means that we have less layers, less elements to go through. So this is how LTE was able to reduce the latency, but you can see from the progression from all the way from release 6 to release 8, it basically keeps lowering the elements necessary. It is similar to release 7, but the terminology changed from there. Starting with LTE, all of the scheduling that the RNC was responsible for is all integrated. So that's the difference. Starting with LTE, all those functions are integrated into the eNode B. Okay, so here is a high level view of the architecture of the EPC. So as you can see at this time, if you have a 2G or 3G network, you can still interface with the new core, and this we call the EPC. So some terminology has changed, and I kind of mentioned them before. So we have the EU TRAN for the radio access network, and you have the evolved packet or evolved core network, EPC. So some things to clarify, you have the serving gateway, which basically interfaces with everything within your network. It's facing all the eNode Bs in a sense. And then you have the packet gateway, which faces the internet. Okay, so here, just reviewing the EU TRAN includes the UE and the eNode Bs. And like I mentioned, the RNC is all integrated at this point. Okay, this introduces the new elements, which comes with 4G with LTE. So like I mentioned, the SGW terminates towards the radio access network. The packet gateway is where you get outside internet access. The MME is where you interface, that the eNode Bs will interface to. And the HSS is basically all the databases. The PCRF, it helps with QoS. And that's not something that we're introducing yet today, so I'm not going to go into too much detail with that. Okay, so to go over some of the terminology, every network operator has a PLMN, which is unique to them. Being that for Baicells, we are all sharing the core with the Cloud EPC, so every operator for Baicells uses the same PLMN. You have the tracking area code. This we're not implementing with our core network yet, but this helps identify where particular UEs are. So this is good if you're paging a UE, you want to know in which area is it located. And then you have two different cell IDs. You have the EU trans cell ID, and this is how the EPC distinguishes which E node B is which. And then you have the PCI. This is how the UE distinguishes which E node B is which. Okay. And then here, the user equipment has kind of two identifiers. You have the IMSI, which is the SIM card. And then you have the IMEI, which is the identity of the actual hardware itself. So this ID is kind of used for if the equipment is stolen, they're able to still track it. Okay, so for spectrum options with LTE, this is, when it first came out, it was mostly just for FDD. And here are, in the US, the different band numbers. Now, FDD spectrum is generally pretty expensive, so most operators, I'm assuming here, won't have this. But anyways, here's a list of the FDD spectrums. Yeah. Yeah, if someone has it, I think AWS 1 is probably the cheapest on here. So,
but
some operators
increasingly, you'll hear, just in general in the LTE world, they'll just call it band 2, band 5, band 48, or whatever it is, and they'll, we're all used to identifying by frequencies or by its common name, but people on this side just default to the number.
Right. And then we have the TDD bands, and I highlighted in yellow the main ones here. So pretty much most operators will have the 365 license, I'm assuming, and that's our main sale is our 1 watt E node B, which is band 42 and 43. So we call it two different bands because CBRS band falls in between those two bands. And actually, the CBRS Alliance was able to get a whole new band approved just for that band, and that's where we have band 48. So once CBRS approved, our hardware will also be called band 48 as well. Anyone that has 2.5 would be in band 41. And 46 is not being used really right now, but is up and coming, and that would be part of the LTE-EU. For 5 gigahertz. Okay, so this is an overview of the frame structure for TDD. So basically, the actual radio frame is 10 milliseconds, and it's split in half, 5 milliseconds each, and then each actual subframe is a 1 millisecond. So in every subframe, you have a downlink or an uplink. And then there's also something called the special subframe, and this is when you switch from downlink to uplink. Okay. The other things to note on here is, yeah. Oh, I do. Yeah. See if it works. Yeah. Okay. So we have the specials. This is the special subframe pattern. And you have different modes. So for anyone that's configured our E node B, you'll notice for special subframe pattern, you have a 7 and a 5. And this is basically your guard period. So keeping it at 7, there's no point really to change this because we have different parameters limiting the distance. But This is one parameter that does affect distance. Okay, and this kind of dives into that too. So you have the subframe assignment is by default set to 2, and this gives you more subframes on the downlink. If you need more uplink, you could change this to 1. And I put the peak speeds of what that looks like. So you could, the aggregate throughput of the base station could theoretically go up to 112 downlink in the default config. If you change that to 1, the downlink drops, but you do double your uplink performance. And I also wrote the cell radius for depending on if you set the special subframe to 7 or 5. Yes. Good.
It's the frame ratio.
Yeah, so, and this is this is also considering category 4 UE, which is the category we're using. So this is assuming that the downlink uses 2 chains, 2 antennas, and that the uplink uses 1 antenna. So that's, so you're half the throughput's, kind of being lost because there's only 1 antenna being used on the uplink. And also, as we talked about before, the uplink is also different than the downlink. And the uplink, because of the power issues, it does also slightly lower the throughput. Here is kind of an MCS chart, depending on what levels you see and what the expected throughput is.
Yeah, hold on that one for a little bit, and maybe spend a little time talking about really what minimum levels people should be considering and that sort of thing.
Yeah, and we'll hit on that a little bit later, but I mean, obviously, you usually want to hit 28 on the MCS for the downlink. So you'll notice here too that it shows 112 megabits per second on the downlink if you're at full modulation. We do have in our current model CPE, however, only has a fast Ethernet connection. So the bottleneck for reaching that is actually with the Ethernet interface. The total aggregate throughput of the whole base station would not be affected, though. And we kind of wrote it out, so 28 is the best you can get on the downlink, and 22 is on the uplink. And this is assuming the default configuration. Again, if you change that to increase the uplink, here are the different MCS levels for that. Okay. All right, so this is a more in-depth look of the actual frame structure itself. We kind of looked at this in an earlier slide, but the one thing to note is that in every subframe, there's actually 2 slots. And then there's something called CP. So there's normal and extended. And this is basically the symbol prefix. So if you need further distance, there's some parameters which will lower this. But the default is normal CP, which gives better overall throughput. This is what one of the resource blocks actually looks like. So in total, I highlighted at the bottom, if you're in a 20 megahertz channel, there's actually 100 resource blocks that can be assigned in a slot. So when the UEs are being scheduled, according on how much data they need and depending on the scheduling algorithm, they will be assigned a certain amount of slots. This is the resource grid. So when you're looking at the different frames, structures, this kind of is what people tend to look at to see where are all the resource elements located. This is more of a lower level. Okay, so in LTE we have something for physical signals. We have the reference signals, which this is how on the downlink and uplink, this is how the equipment knows what the signal strength is. They base this off of the reference signals. And then you have the synchronization signals. So this is how the UE is able to find out what the timing of the frames are. Okay, so the UCI, this is what the UE uses in total to inform the eNode B of the metrics it's getting. So the UE will inform the HARC, which will be able to tell how many messages were acknowledged and how many weren't acknowledged. It will be able to submit the CQI. The RI, the rank indicator, is how many layers that it has. PMI is more detailed information, which is for closed loop operations, which we're not doing yet. And then the UE will also do schedule requests. So to break down into that, so in the HARC feedback, the UE will send the total amount of messages, and it will say how many that it was acknowledged and how many was not acknowledged. And this is able to calculate blur. So in LTE, blur is the block error ratio, and this is how we're able to determine how good the signal is in the transmission. In LTE, you typically want less than a 10% blur. Then you have the CQI feedback. So for anyone that's using the beta software, you'll notice that on the main page of the eNode B, it actually shows a CQI for each UE. And there's a CQI index up to 15, and this basically indicates how good the transmission signal coming into the UE is. And the eNode B will use this information to determine what MCS levels to assign to the UE. Okay, then you have the rank indicator. So this basically says how many antennas do I have. So we have, with our current models, we have a 2x2, so we have 2 antennas. And so in most cases, the UE will report that it has a rank 2. If there's a lot of noise on one of the antennas, it's possible that it could indicate a rank 1. So in some cases, that can help also determine noise. And then you have the PMI, which is for closed loop. Okay, so when the UE powers on, this is the initial procedure. It will first do a cell search and selection. It receives the system information, and then it's able to get the random access procedure. So during the cell search process, the first thing it needs to determine is what is the PCI. And the PCI, we'll go into details a little later on that, but it's broken into the PSS and the SSS. It adds these two IDs together. And once it does that, it can determine where are the reference signals, where are the synchronization signals. And what is the bandwidth size, and how many antennas. So this is how it determines the cell. It also, during this time, if there's multiple cells detected, the UE will generally always pick the strongest signal.
How long is that initialization?
Sure. Yeah. Yeah, it's pretty quick, I think. It depends on the UE chipset and all that. Okay, so this is, and Cameron will kind of go into this as well in a little bit more detail later, but this is basically the PCI. So you have the PSS signal, which has 3 IDs. This determines where the reference signals are located. So it's important that when you're deploying your equipment that not only do you want to channel plan, you want to PCI plan. Again, we'll go into a little bit more details later, but in total you have 504 PCIs. Information about the cell. I don't think we need to go into too much information here, but the point being that after this, at this point, the whole time the UE is just hearing, it's only receiving. So at this point, it now has enough information to start the transmission. And to do this, it needs to do random access first. So random access is a contention-based, where it's not exactly scheduled yet, so it kind of competes during this time to connect to the eNode B. Once it's finally connected, then it knows all the synchronization and is able to be scheduled at that time. Okay, so after the UE finally attaches, it's going to be assigned bearers from the EPC. And this is high level of what that kind of looks like. So you have the actual bearer is between the UE and the packet gateway. And then you have different bearers in between that. But there's basically two different bearers. There's the guaranteed bitrate bearer. So for certain applications or certain business customers that you need to guarantee a certain service, there's bearers for that. And then there's the non-guaranteed bitrate one. So there's always going to be a default bearer, and the default bearer will always be non-GBR. So for Baicells, there's going to be one bearer sign that's default, and it's non-GBR. In the future, we plan to implement the ability to create more bearers for different types of services. Okay, so this goes into kind of the terminology when it comes to the bearer. So you have an APN, and you'll notice that in the UE, you'll get an IP address under something called APN1. So this indicates that there is one APN, and that's where the IP address comes from. If you have multiple, you can have multiple bearers in a single APN. So with one IP address, you could have multiple bearers for different applications. You can also have multiple APNs as well. So one thing that we're planning on doing in the future as well is to create multiple APNs, multiple IP addresses, because currently you just have one IP, and the challenge is with that you can't assign a separate management IP, which is popular in the WISP network. So with the beta software, if you look at the last term here, UE Amber, this is what is the bit rate, maximum bit rate allowed between all of the bearers, all the non-guaranteed bit rate bearers. So with the beta software, right now, you're able to actually rate limit customers. And what this does is with the bearer, it assigns a UE Amber. And this is how we're able to currently rate limit with the Baicells equipment. And this is yeah. Okay, so this kind of just goes through high-level overview of what that looks like. So for example, if you had two APNs, you can, with each APN, like I said, have multiple bearers. You'll notice that the UE Amber means that across all non-guaranteed bitrate bearers and all APNs, that it will be rate limited to that specific rate. Okay. All right, now we'll talk about the schedule request procedure. So whenever the UE needs to send data, it needs to request this first. So this kind of shows a diagram of that process. And currently with LTE, you'll notice that it could take up to 20 milliseconds for this to happen. So that's kind of where the added latency comes from. So one thing is, if it's denied, so the UE is going to schedule a request. If the UE is too busy, or the eNode B is too busy, it's possible that it won't be it won't be granted that request. So there's certain timers that can take place, and it could take a while. So we've noticed with a couple operators that have higher interference issues that there's been issues sometimes where the UE might drop out, it seems, or bottom out, where there might be a period of time where it's connected, but it loses internet access. And this is one example of why that may happen. So if there's high interference, there's potential issues where it might not be scheduled because either the NOB is not hearing that right, or we'll talk about that a little bit later in detail as well. With LTE, you can actually assign different scheduling algorithms. So by default with LTE, with our product, we're using round robin. So this is the most simple scheduling algorithm. It's just first come, first serve. It's not very complex at all. There's also a couple other ones that you can use that we are currently implementing. I think the one that would be of most interest would be maximum throughput, because this will basically assign the highest priority to the best connected users. So if you're looking for the best total aggregate throughput, maximum throughput would be the best scheduler to select. The other one, PF, is a little bit more complex, but it kind of averages, what throughput they're getting, and then as well as puts into equation the MCS levels. So it tries to be a little bit more fair with that. Okay, so one thing that's a little bit different too is the uplink power is actually controlled by the E node B. So, and if you could think, with your cell phones, you always, they want to make sure the power is always low. So if there's no traffic going across the link, you'll notice that the TX power is typically dropped down. And so what the E node B does initially is it will set a target SINR. So the UE will increase power until it reaches it. And at that point, the power depends on how much data is being pushed. So if you are recording what the MCS levels are during installs, one thing I would recommend is check what is the uplink MCS while running an uplink speed test, because that's going to give you the most accurate MCS readings. Okay, so here we'll talk about the basic signal measures with LTE. You have the typical RSSI, which most are used to, but in LTE we introduce RSRP. Now this is the actual power of the reference signals. And the difference with RSSI and RSRP is RSSI is more of a wide band approach. It will determine what is the signal power across the whole reference signal resource block, where RSRP only cares about the one little resource element. So that's why the RSRP is a lot weaker. It's only doing a narrow band approach for receiving signal. RSRQ just takes an equation of the RSRP and RSSI to help determine if there's any issues. It's basically the quality of the signal. So the other point being that RSRP, it does a better job at knowing what is the signal of a particular sector. So assuming that your PCI planning is correct, you could have noise from other sectors, and RSRP would help eliminate that. So it's able to determine what is the power of that particular sector. So it's a little bit difficult to determine if there's interference with RSRP, but it does determine what the actual power it should be receiving is. Okay, so this is kind of a diagram of the differences here. Like I mentioned, you'll see in the yellow highlighted area shows this is where RSSI would measure, and RSRP only cares about the actual elements itself. So it's a more narrow band read. The other signal measures are SINR and CINR. So typically, and at least with our equipment, they're very similar, and for the most part, they'll pretty much be the same. The one thing that the CINR, and that's typically in LTE what we'll ask for, what is your CINR? The difference is that CINR, for the most part, tries to mitigate the interference. If the two signals are like drastically different, that could indicate that there's some interference issues, but for the most part, they'll be the same.